Is age a predictor of male waist sizes? As men age, their metabolism slows, so it makes sense that as men age, their waistlines expand. Use the data below and a 1% significance level to test for a positive linear relationship between age and waist circumference in centimeters. So we have the sum of squares values for all the terms, xx, xy, and yy. That's very helpful. And we have our raw data here. One thing we need to do is count up how many pairs of values we have, because that's going to be our n for the problem. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's try to remember that n is 14 in this problem. Now the problem asks us to test for a positive linear relationship between age and waist circumference. So we're testing for a positive relationship in the problem. Now, positive linear relationship, of course. So in this problem, the first thing we want to do then, of course, is to come up with the claim. So let's go ahead and do that now. The claim in symbols, of course, is going to say that the slope, beta 1, is positive. So the claim should be worded so that it says beta 1 is greater than 0. Then from there, we're going to get HO and HA. Now, looking at the fact that this is a greater than symbol, it's one of HA symbols, HA and the claim will be the same. HO will, of course, be the opposite idea, less than or equal to 0. Then let's do our data step. Remember, this step is quite involved, but it's not too bad. So let's start out with the first thing. We said that we should remember that n is 14 for the problem, and that alpha here in the problem is given as 1%, 0.01. We'll need both of those later. The next thing we should do first is to come up with the slope. So we want to do beta 1 hat, the point estimate for the slope. Okay, so now we're going to plug that in as sum of square xy, the mixed term, over sum of square xx. Now looking at our numbers that were provided to us, we have the sum of square xy as 1104.007143 divided by sum of square for xx, which is 3811.214286. Okay, so those are all the digits they gave us. Let's go ahead and do the division then and come up with our slope for the problem. Okay, so we'll have 1104.007143 divided by 3811.214286. And when we're done, we get the answer 0.289673 ... All right, I'm going to go ahead and store that into my calculator under x. So x for us will be the same as our slope. All right. Okay, so I have that stored in there. Let's go or do our next step. Our next step is going to be to come up with the sum of square for errors. So that's SSE. Sum of square for error has the following relationship: SSYY minus beta 1 hat times SSXY. Okay, now that SSYY value is given to us. It's 942.00355714 times our slope times SSXY. Now our slope is 0.28967. I'll just put that in there for now so we have room to write the next term. And the next term is SSXY, the same number we have on top of that fraction there. That's 1104.0071, let's say. Okay, now let's enter that stuff in and see what we get for SSE. Okay, so we're going to have 942.00355714 minus the slope times 1104.007143. And when we're done, we get 622. So 622.2021432. So that's our sum or square for error. All right, I'm going to leave that in my calculator because we're going to need it in just a second. Our next step is to come up with the S value for the problem. So S, which is going to be the standard deviation for the error term, or an estimate of the standard deviation for the error term, we're going to have that as SSE over n minus 2. Now, SSE we have above, right? So that's 622.202 dot 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 divided by 14 take away 2, which is 12. And when we work that out, we come up with, so I already have that number 622 in my calculator. I'm just going to divide it by 12. And then I'm going to take the square root of it. Taking the square root is the same as raising it to the half power, so I'm going to do that. It's a little faster in my calculator, so it gives me 7.2007 dot dot dot. I'm actually going to store that value into my calculator for a minute. I'm going to store it under S, just temporarily, and then I'm going to eventually, of course, actually let me store that under S. I didn't do it right, but I'm going to now. So it's 7.200706813. So I'm going to store that again under alpha S in my calculator. I'm going to erase that in a minute when I use it for the next step, but for now it's stored there as S. Okay, now the final step of the data process that we're going to do is to come up with something called S beta 1 hat, or the standard error for beta 1 hat. So S beta 1 hat is basically a simple formula. It's going to be the S we just had in our calculator divided by the square root of SSXX. Okay, so that S that we just calculated, which was 7.2007, so 7.2007 dot dot dot, divided by the square root of the denominator here, which is 3811.214 dot dot dot, right? Let's do that calculation and see what we get. Okay, so I still have that number in my calculator. I'm just going to hit divide by the square root of, and the answer is going to be 3811.214286. So that's the value that I put in for SSXX. Close it up, hit enter, and I get the final result for this guy as 0.1166389 dot dot dot. So it goes on and on and on. But we have enough decimal places there, I think. So there is our S beta 1 hat and our beta 1 hat here. Okay, so those are our values that we're going to need for our test statistic in the next step. So let's go ahead and get a new sheet of paper out and work out the test statistic. Okay, so our test stat formula is quite simple. Remember, it's a t-test stat formula. And it's a simple fraction. It's beta 1 hat over the standard error for beta 1 hat. All right, now beta 1 hat we had here as 0.289673 dot dot dot, right? And then that was going to be divided by S of beta 1 hat, which we have the answer here as 0.1166389. So 66389 dot dot dot. All right, let's work that out in our calculator. And I did store these values in my calculator, but let's actually go ahead and just type in what we have there, because I just want to show you that, of course, if you have enough decimal places, you don't have to have a store feature on your calculator. Certainly, at this point, with all those decimal places, we won't be very far off in our answer, even if we do round a little bit or truncate a little bit. Okay, so we hit enter there, and we get 2.484. 2.484. So 2.484. So that's your t-test stat value. All right, now our next step is to compare a test stat against a critical value. So because we have a t-distribution, we'll draw a bell curve here. Centered at 0 as always. And we look at the HA and determine that it's a right-tailed test because that symbol is there pointing to the right. A greater than symbol means we're dealing with the test stat falling on the right-hand side when we reject the null hypothesis. So it falls past the critical value, we'll reject the null hypothesis. And we have this critical value here that we need to look up. It's t.01, that's our alpha, right? All that alpha will be thrust into one tail, so we're just going to use t.01. And the degrees of freedom here is going to be 14 take away 2, or 12. So remember, it's n minus 2 for the degrees of freedom in this problem. So let's go to our t-table, look in the 0.01 column down to degrees of freedom 12, and find out what our critical value is. Okay, so we're looking for 0.01 in one tail with 12 degrees of freedom. We find the answer 2.681. Okay, so we found our critical value to be 2.861. 2.861. Now, with that critical value, when we compare that against our test stat, we see our test stat doesn't quite make it into the rejection region. It's just a little before that point. And so we're going to be in the white space here. So we're going to say, do not reject HO. And therefore, do not support HA. All right, now look at our claim and realize that our claim is the same as HA, so we'll be using the phrase do not support. So the sample data does not support the claim. The sample data does not support the claim. So again, the test stat's not too far from the rejection region. So it could be that if we had a different alpha value or a larger n, we might have been able to show that there was a positive linear relationship. But with this data right now, it's just not strong enough to conclude that. So perhaps if we had a larger sample size, or if we had a different alpha value, we might have been able to reject the null hypothesis. But here we weren't able to. So at this point, we cannot assert that there is a positive linear relationship.